Module 3, Programming and Interfacing of 8051 Microcontroller. So okay, let's begin with our first topic. It's simple programming examples. We'll be discussing a few assembly language programming in 8051. It will be very simple. Let us begin with our first example. Exchange the content of 6 of H and F of 0H in 8051 microcontroller. So two memory locations are given here. So the content of these two locations we need to exchange. Okay, so microcontroller is mentioned here. F of 00H is actually outside the microcontroller and 6 of H is internal to the microcontroller. So our program logic is, we have the memory location, internal RAM location, say 6F internal, and in external memory, okay, we have a location F of 00. Okay, there is a content here, say C2, and this content C1. We need to exchange them, C1 to here and C2 to here. Okay, so what is the first method? We have to get the data from what you call the external memory location F of 00H. So external memory location access, we can use the instruction MOVX. Okay, and internal memory we can access as a direct addressing mode. Okay, so to access the external memory F of 00H, we should load the content F of 0 to F of 00 to the DPTR. So the instruction to copy F of 00H to what you call the DPTR is move DPTR at where move DPTR, load DPTR with this content F of 00H. So comma hash 0 FF00H. So the content F of 00H will be copied, DPTR will be copied with the F of 00H. Okay, now we need to get this data to the microcontroller. So the transfer of data from external memory will be through the accumulator. So we can use the instruction MOVX A, at DPTR. So what will happen after executing this instruction? Our accumulator, so let it be capital letter A, our accumulator will be C2. Okay, while after executing MOVX A, at DPTR, our accumulator will be loaded with the C2. Now we can take the data to any of the register from 6 of H. Okay, so before copying this accumulator or C2 to C1 or 6 of, we need to save the data at 6 of. For that we can use, say, register move R0, 6 of H. So after executing this instruction, our register R0 will be the content C1. Okay, now what we need to do, this accumulator content we need to place at 6 of. For that we can use the instruction move 6 of 6 of H, accumulator. So accumulator content will be copied to 6 of. So after executing this instruction, the register memory location 6F will be C2. Now we need to take this R0, which was C1 or content of 6F, to the external location F of 00H. So for that we need to bring R0 to accumulator. From R0 to external memory movement is not possible, so we can use move A, R0. So accumulator is now C1. That C1 we can transfer to the external memory using the MOVX instruction. So MOVX at DPTR, A. This will make F of 00H with C1. So after all these instruction, our result is what? Our memory location 6F will be, memory content 6F will be will be C2 and memory location f of 00 will be C1. That is what exchange the content of 6f and f of 00h. Okay, let's begin with continue with our second example. Hope you understood this program. Very simple program it is. Second question, treat R6 and R6 R7 and R4 R5 as two 16-bit registers. Perform subtraction between them. Okay, and store the result in 20h and lower byte in 20h and 21h. Actually, this is 16-bit subtraction. We did this type of subtraction in theory class. So we have the content R6 R7 and R4 R5. So memory location okay, so R4 R5 R6 R7. So R6 R7, so R4 we can treat R4 as lower bytes, R4 is lower bytes and R5 is higher bytes. So again here lower bytes, here higher bytes. After the subtraction we need to keep the result lower byte at 20 and upper bytes at 21h. So subtraction is very simple. We can use the instruction SUBB, subtraction SUBB a comma register. Okay, so hope you remember the theory topic. SUBB will subtract carry also. So before doing the subtraction on lower bytes, we should initialize the carry to 0. So first step in our program is CLR CY, which makes carry flag is equal to 0. This instruction is very important because if we start with the main next line, and if any of the instruction before made the carry flag 1, it will subtract 1 also from the lower bytes. So before that we should clear it, carry flag to 0. Now to subtract, we should take R4 lower bytes of the subtrahend to the accumulator or any register. So move a comma A comma R4. So this instruction will make accumulator is equal to R4. So what was our R4? It was lower bytes. Next, then we should take the next 16 bytes lower bytes, which is from R6. So here let us subtract R6 R7 from, we should do R4 R5 minus R6 R7. Okay, so R4 R5 R4 minus R7 R6. Okay, let's R4 is the lower bytes. So let us subtract what to do here, R6 from R4. So instruction is SUBB subtract a comma R6. So a is equal to R4 minus R6, and that result will be available at the accumulator. So if there is a carry during the lower byte subtraction, that will be available within the carry flag. So we don't want to modify whatever the carry after the subtraction, we need to keep it as it. But here now the accumulator is having the result of R4 minus R6. So before doing the higher byte subtraction, we should save them to some register. So that register is given here, store the result in 20h lower bytes. So that lower byte is already there in the accumulator, we can move it into the 20h. So move 20h comma accumulator. So what the result here, 20h is equal to lower bytes of result. Lower byte of the result is there. We saved already to the 20h. Okay, next we need to subtract the higher order bytes. For that we need to bring R5 to accumulator. So the instruction is move a comma R5. So move a comma R5 ചെയ്യുമ്പോൾ accumulator എന്ന് പറയുന്ന ഇപ്പോൾ R5 ആണ്. Next we need to subtract R7. For that we can use the instruction subb a comma subb a comma which instruction R7. So R7 ചെയ്യുമ്പോൾ R7 a is equal to R5 minus R7. Okay, so that result will be available within the accumulator. That we can copy to higher order bytes in the 21h like copy am. So move 21h comma accumulator. So our result 21h is equal to higher bytes of the result. Okay, so if there is a carry, that will be available within the carry flag. Anyway, that is not mentioned. Higher order bytes and lower order bytes only mentioned in the subtraction result. Okay, so that's all about the simple program to subtract two 16-bit numbers. First we need to before doing subtraction within the lower order bytes, we should clear the carry. That is the important point to remember here. Next, store the higher nibble of R7 in both nibbles of R6. Store the higher nibble of R7 in both nibbles of R6. So question is very simple. So we have register R7. Say let it be 7F. Okay, we need to copy the higher nibble which is 7 to both the nibbles of R6. After executing our program, say this is our R6 register, higher order nibble is 7, that is to be within the both nibbles of R6, means it should be 77. Whatever be the content of R7 which with higher nibble should be loaded to the both nibbles of R6. That is our question. Now how to start with our program? So our data is from register R7. Will let us take R7 content to the accumulator. So the command is move a comma R7. After executing this result, our accumulator is equal to R7, which is equal to 7F. Whatever be the content, it will work fine. Okay, now we need to take the higher order bytes only. So how we can separate the higher order bytes? We need to mask, we need to clear the lower order bytes of the accumulator. For that we can use the AND instruction, ANL a comma. So 7F is how it looks like, 0 1 1 1, then F is 1 1 1. After executing the instruction here, this should not change, and at the same time this should change to 0 0. For that we can do the AND operation, say 1 1 1. Okay, 1 with 1 dot A makes 1 only, 0 dot A makes 0. So here 0 0 0. So what will be the AND operation between them? 0 dot 1 is 0, 0 dot 1 is 0, 0 dot 1 0, 0 dot 1 0, 1 dot 1 1, 1 dot 1 1, 1 dot 1 1, 1 dot 0 0. That means 7 0. Okay, we got 7 0 here. So the data to be AND with the accumulator is F. This 1 1 1 is F and this is 0. So ANL A comma hash F0 H. Sometime we should keep 0 here also. So after executing this result, this instruction, our accumulator will be 70. Will be 70. We have now the higher order nibble of the R7 register is in the accumulator. Now question is, this 7 should come to both the nibbles of accumulator. So 70 if you keep to the R6 register, we can make the higher order nibble at a higher order nibble of R6. So we can do move, so A is equal to 70 here, move R6 comma A. this will make R6 is equal to A, which is equal to 7D. So higher order nibble is already with 7 only. Now we need to get the 7 to the lower order nibble of also. For that, what we can do to get it 7, what we can do here is can use swap instruction. So swap will exchange the nibbles of the accumulator. So swap A, what swap A will do here, A is equal to A is 70 here. After executing swap, 7 will comes here and 0 will go here. So it will be 0 7. Okay, now this 7 only we need to bring to the accumulator, 7 only. So we don't know what is actually 7 or some other data here. So 7 we need to bring to the R6 of lower nibble of the R6 register. For that we can do OR operation between accumulator and the R6. So ORL A comma R6 will make, let us check what will happen. What is A now? A is 0 7 0 7 is 0 0 0, 7 is 0 1 1. But now R6, what is the content of R6? It is 7D. So 7D is 0 1 1 1, then 0 0 0 0. If you do the OR operation, 1 plus 0 1, 1 plus 0 1, 1 plus 0 1, 0 plus 0 0, 1 plus 0 1, 1 plus 0 1, 1 plus 0 1, 1 plus 0 plus 0 0. This is 7, this is also 7. So after executing this instruction, our A is equal to 7D 7. Okay, this 77 should bring to the R6 register. That is what our question. So the instruction to do so is move R6 comma A. This will make R6 is equal to 7 7. Both lower nibble and the upper nibble of R6 is now 77. So the 7F is my own example, my own content. Whatever be the content, it will follow the content. The higher order nibble of R6, R7 will copy to both nibbles of this R6 if you do these instructions. Hope you understood. Next, transfer the block of data from 20H to 30H. From 20H to 30H to external location from 1020 to 1030H. So it is mentioned here, this is from internal memory and this is from the external memory. So we have the block of data transmission. So internal memory is from the location 20 to 30 and we need to transfer this block to the external memory ranging from 1020 1020 to 1030. Okay, so 20 internal copy to 1020 external, 21 internal to 21 external, etc. So we need to do this transfer. Okay, that is what our question. Now what we can do, how many data? So see here we have 20 data from 20H to 30H. So 20H to 30H consists of 16 locations. So 20, 21, 29, then 2A, 2B, 2C. So 16 locations are there actually. So treating or getting the data by mentioning individual address is difficult. It will consume more memory space and the program is not a good logic. Okay, so let us do our program by initializing a counter. So 16 in memory. 16 is actually, what is the number 16? It is 10. So let us take one register to keep the counter. So example R7. So move R7 comma hash 10 h. This 10 is actually 16 in decimal. Sorry, 16 in decimal actually. 10 in hexadecimal is 16 in decimal number. So our counter is equal to 16. Okay. Then we need to get the data from 20. Then that we need to send it to 1020. So move R0 comma hash 20h. So we can take 20 first block, first location to the R0 register. We can use index addressing, sorry, indirect addressing here. So move R0 comma at hash 20, initialize R0 with 20. So this is what this instruction. Now we need to initialize the DPTR with 1020 to have the external data transfer. So move DPTR comma hash 1020. So after executing this instruction, our DPTR is equal to 1020. Okay. Now we need to get the data from 20h. For that we can use the instruction move a comma at R0. So a is equal to content of memory pointed by R0, which is content of 20 time being. So this accumulator is now having the content of 20. We need to move it to the 1020. For that we can use move x instruction. So move x, which location? At DPTR. From where? From accumulator. So accumulator, whatever the content of accumulator, that will transfer to 1020 this instruction. So 1020h is equal to 20h. Content of 1020h is equal to 20h now. So we transferred from 20 to 1020. Now we need to point to the memory location next one, which is 21. Same time external memory also 1021. For that we can use INC, which register R0. Content of R0 is incremented by 1, which will make 21. Also we need to make the content of DPTR by 1. For that we can use INC DPTR. So DPTR R0 become R0 plus 1. DPTR is equal to DPTR plus 1 after this instruction. Then we need to check whether we transfer this 16 location. For that we can use the instruction decrement and jump on non-zero. Decrement and jump on non-zero, where our counter is at R7. So R7 comma, where do we need to do the transfer? It is to get the data from R0. So here we can use a label, say repeat RPT. So to where it should do the transfer? To RPT. So DJNZ R7 comma RPT. So at time being during the first loop R7 was 10, then here it become 0f. It is a non-zero value, it will take to here. So for that R0 is now 21, DPTR is 1021. It will do the exchange of data there. Then it will increase to 22 and 1022. Decrement R7 by 1, so becomes 0D. Sorry, 0E. Again a non-zero value. Again it will do the transfer of data from 22 to 1022, increase to 23 and 1023, now decrease by 1, so it's become 0D. Then again transfer data from corresponding location, then 0C, again 0B, then 0A, then 10. Again it will do transfer from 0A, sorry, 22A to 1002A. Then again do the decrease by 1. It will continue this operation until R7 becomes 0. Once R7 becomes 0, it will break this loop and come out of. Then there will be some instructions follow these loops. then it will continue. So by the time it will be transfer the data from 20H to 30H to the external memory 1022 1030. Hope you understood this simple instruction, simple logic, simple program. Okay, then let us move to the next program. Find out how many equal bytes at corresponding locations between two memory blocks 10H to 20H and 20H to 30H. So what this question is saying, find out how many equal bytes at corresponding locations between two memory blocks. So we have two memory blocks 10H to 20H, 10 to 20. We have a block of data from 10 to 20. So 20 is not included here. So up to 1F only, our data. Okay, then 20 to 30. 2F. So 20 to 2F is actually 16 locations. 10 to what is this? 1F. This is 1F. 10 to 1F is actually 16 memory location. 20 to 2F also 16 memory locations. Okay, so how many equal bytes at the corresponding locations? So if check 10H and 20 are equal or not. If they are equal, increase the counter. Then 11 and 21 check. If they are equal, increase the counter. So corresponding locations we need to do the checking. If the locations have the equal data or same data, we need to increase the content of a counter by 1. For that, let us take a counter. To keep a counter, let us take a register R7. So the instruction move R7 comma hash 00H. This will initialize the counter. R7 is equal to 0, which is a counter. Okay, to count how many equal bytes are there. Now we need to do the comparison from 10 to 20. So first initial location of the first block is 10 and the initial location of second block is 20. So let us take them to R0 and R1. So move R0 comma hash 10H. So we pointed R0 to initial location of first block, then move R1 comma hash 20H. R1 we will take to first location of the second block. Now to do the comparison must be performed within the count. For that, before that, let us do we need to have a number of bytes. So number of bytes in the memory block is 16. So let us take the number of bytes contained in say R6 register. So move R6 comma hash 10H. This is number of data. Number of data is 16, which corresponds to 10 in hexadecimal. Now let us take the content of 10 to the accumulator. For that, move A comma at R0. So A is now content of 20. Content of 10. Now we can perform the comparison. So comparison is from data 20. So for that, let us take the content of present accumulator to say register B. So move B comma A. B is equal to now A, which is content of 10H, because indirect addressing is allowed within the accumulator only. That's why we have used B here. Then we will take accumulator with 20. So move A comma at 21. Sorry, at R1. So A is now the content pointed by R1, which is the content of 20. Then we need to do the comparison instructions. Compare and jump on not equal, CJNE, which are all the registers to compare A, B. We are performing 10H and 20H are equal or not. So let us find the label here. If they are equal, we need to increase the counter. Where is the counter? Here in R7. So if the counter is INC R7, if they are equal, it will increase, otherwise it will skip this instruction. That's why skip instruction is here. Say skip instruction is here. So A, B, skip. So CJNE A, B, skip. So INC R7. So if the two locations or the content of A and B are equal, it will not perform this skip, so that it will execute INC R7. So they equal means we will increase the count by 1. So INC R7, and the skip is we need to perform the take the data from next memory location. For that, content of R0 and R1 we need to increase. So what we will do here, INC R0 and INC R1. Now the memory is pointing to 11 and 21. Then we need to check whether we completed 16 locations. Same logic. Then decrement and jump on non-zero, where the count is in R6. R6, what we need to do here, we need to take the data again, move A, R0. So here is our RPT. So the transfer should be to the RPT. So now take data from 11 and 21, perform the comparison. If they are equal, increase the count by 1. Then otherwise skip to here, point to the next memory locations, decrease the count of R6 by 1, perform again once until R6 becomes 0. So this is about the simple program.